Hello, good morning, Professor.
Morning.
Hi, Professor.
Morning, Professor.
Morning.
Hello, Professor.
Hi, Nur. So, Nur and Manar, have you been to Seoul before? No? So this will be your first time. How about
For me,
subway?
it's the second time.
Your second time. Good.
Mm.
Hi, Sunyo. How are you? Okay. And then just we need one more person. Hi, Sunyoung.
Hi.
So
Hello,
did you have something last class? I think that you were absent.
Yeah.
And what happened?
I couldn't wake up in the morning.
Sometimes I regret also that why did I set my class for 9 a.m. because I also had to very hurry up in the morning. So I usually wake up like 7:30 a.m. and then try to have a walk for like 30 minutes at outside, and then come back and then have a kind of brief breakfast, and then take a shower and then come to the office. So it's very tight schedule for the morning for me also. And maybe next time for the starting at the 10:30. But the problem is that for the second class and third class, the problem is sometimes the faculty members are going outside for the lunch, but it is in general like 11:40 or 11:45, so a little bit early. So if I have class in the second time, which is finishing at 11:50, then I cannot really join them. And also if I have class at starting from the 1 p.m., you can imagine that lunchtime can be longer than 1 hour. So in that case, also I cannot join them. So either like 9 or starting from 2:30 or maybe even 4 will be probably the best. But if I start at 2:30, then that time is like after lunch. So many people are feeling sleepy. So, okay, then what time should I, have my class? Maybe it will be for the 4 for the next time. So I don't know which class time student prefers. Kali, how are you? 9 a.m. is the best for you? Really?
Or 10:30, Professor.
Okay. How about Seungyeong? What time is going to be the best?
I prefer the 10:30.
Oh, 10:30. How about you, Jew?
I prefer 10:30 or 4 p.m.
Oh, how about you, Manar?
10:30 is better.
Good. Also, you prefer 10:30? Okay. So
Oh,
I guess it's kind of competition, among faculty members who said first, because we do not really want to have all the class in the same time. So we want to make it spread so that student can select multi classes from the same department. Otherwise, you can select only one class and you cannot, choose another class, which we should avoid. So if somebody has a class at 9 a.m., I think that other faculty members are thanking that professor. Oh, thank you for starting at the 9 a.m. So last class was photochemical interaction, and the major two things are the photodynamic therapy and also photostimulation, biostimulation there. But in other words, low-level laser therapy, or these days, low-level light therapy. And also, if you are using the light for giving a stimulation for the brain, then it is also called as a photobiomodulation. So photobiomodulation is more preferred kind of terminology for the brain light stimulation. But all other applications of light to the tissue using the low level power is going to be called as a low level light therapy. How are you, Ji-hoon?
Sorry, I'm late.
Okay, so we were having a discussion about what time will be the best for the graduate school student. So what time class do you prefer? June. Do you like 9 a.m. class?
Actually, nobody wants.
Oh, I had one student. Carly wanted to have a 9 a.m. But so which class time do you prefer to have? Jiun, can you hear me?
Yeah.
Yeah, so
Yeah.
which time? No class.
I think it's hard to change it now.
I
Because
mean,
it's
not
about
this
the hard
class, not this class, but for the future.
future.
Mm-mm-mm.
Maybe afternoon is the prefer.
Afternoon. Oh, I see. I was actually reading an article. It was saying about the effectiveness of using your arm or hand during the class, and that they can actually make the participants or students can pay more attention for the class, such as if it is good, then you can have a like O, and then if no means that like no, and then there were like about 8 kind of signs that you can show during the class. I thought I downloaded that one, but I cannot find it. But anyway, we can just start. So, Ji-hoon, can you briefly tell us about what is the photodynamic therapy?
Photoscience therapy. I don't remember exactly, but it's give a low level laser to the tissue and activate the metabolism activation.
I think you are talking about the biostimulation.
It's different.
Yeah. How about you, Seung-young? Can you tell us briefly about the photodynamic therapy?
Mm, uh, using the laser, I remember the mitochondria.
That's also about the biostimulation or low-level light
Ah,
therapy. Yeah. How about garlic? No, garlic. Manar, don't disappoint me. No, Manar.
Professor?
How about you, Nur? Oh my God. Then am I just kind of talking myself during the class? Oh no, it's a serious problem because students don't remember anything from the previous class. Oh, okay. That proves that I'm not a good instructor. Oh. So today we will start to talk about the thermal interaction. So before starting thermal interaction, suddenly I'm showing about the H&E staining. So you may kind of wonder, oh, why suddenly H&E staining? So I'm sure Seung-young must be familiar, right, about the H&E staining. But maybe Garlic, Manar, and Jae-woo, and Ji-hoon, and Nur, you may not familiar. Am I right? So I'm going to briefly go over about the H&E staining because you may have a chance to see this H&E stained tissue in the future. Or Seung-young, actually, can you tell us briefly about what is the H&E staining?
Professor, I'm sorry, but I couldn't heard
Oh, what's your
this.
background for the undergraduate?
Physics.
Oh, sorry. Okay, so you are not also familiar. Okay, so nobody here has a life science background. Okay, I see. Oh, here is the Taehyun. Taehyun is the researcher at the EPRI in our school. And then I think he's now serving as a military service by doing the research at the EPRI. So hi, Taehyun, how are you? Oh, you don't want to show yourself to everyone? Taehyun, can you hear me?
Yes.
So you don't want to show yourself to other students? Oh, what is this? It's very blurry. Are you okay? Are you alive? Are you human?
I think it.
Do you feel 영어로 하는 게 좀 힘들어서 그래요?
네. 아니요, 그 비디오 카메라가 안 좋은 것 같아가지고요.
Aha, I see. I mean that your current video reminds me about something in the kind of in our body, looking at the endoscope and then looking at some maybe stomach or intestine using the endoscope. Anyway, so Taehyun is going to audit this class because he also doesn't have some idea about the biophotonics. So that he asked me for the permission to take this class as auditor. So anyway, I go back to the H&E staining. I thought maybe Seung-young is having a background in life science, but I realized that you are also having in the physics undergraduate. Okay, so H&E staining is the full name is hemoctocene and the eosine, and this is the most basic staining technique for the sliced tissue to look at the tissue. It is because the cells in our body, when you are looking at that, very thin slice, it has no color. It's kind of transparent. So if you look at the microscope for the sliced tissue, actually you cannot tell anything from there because it's transparent. So there are two types of dyes. One is the acidic dyes, the other one is basic dyes. And the acidic dyes is reacting with the cationic or basic components in the cell. So in our body, the proteins and also other components in the cytoplasm. So cytoplasm is kind of fluid, filling the space inside of the cell. And those protein and the cytoplasm are having a basic property. And then that can bind to the acidic dyes. So another way is cytoplasmic protein. They are acidophilic, which means that they prefer to bind with the acidic dyes. And then compare with those cytoplasm in the proteins, other components in the cell, such as the nucleic the acids. These are acidic, and therefore they are going to bind to the basic dyes. And another way, of course, they are basophilic. So in English, if you have a philic, that means that like. So we can have a hydrophilic. That means that hydro is water and the philic, water-like. And then lipophilic means that like a lipid. So hydrophilic property means that they prefer to bind with water. And the lipophilic means that they prefer to bind with lipid or fat, basically. So the eosine is an acidic dye. So therefore, they will bind to the basic component, which is the cytoplasm. Eosine is having negatively charged. So they are normally having sodium plus some dye, and then overall they are going to have negative ions. And then they can stain the basic structure, and then making color as a red or the pink. So that sometimes it is called as a eosinophilic. So cytoplasmic filaments in the muscle cells or intracellular membrane or extracellular fibers and collagens, and then red blood cells are going to be stained with eosine. So red blood cell will be stained as a bright red color. So here you can see these red colors. You can see those. Those are representing red blood cell in the blood. And then the other pinkish color here, you can see lots of pinkish color. And those pinkish colors are mostly representing extracellular fiber or sometimes collagen, or it can be in the cytoplasmic filaments. Compared to the eosine, the hematoxylin is a basic dye, and then it has a chloride plus some dye. And then hematoxylin is also actually called as a hematine, which can be obtained from the tree and then combined with the aluminum ions. And then it will be also going to use to stain acidic because this is a basic dye. And then making the purplish blue. So the DNA in the nucleus or RNA in ribosome or rough endoplasmic reticulum, they can be stained as a purple color. So if you go back here, you can see this kind of dark blue or those bluish thing. Those are basically mostly actually representing the nucleus in the cell. So when you look at this, you can actually count as a 1 cell, 2 cell, and 2, 3, and 4, and 5, like that. So you can count cells by looking at this bluish color. So now we will start to talk about the thermal interaction between the laser and our tissue. So our body temperature is around 37 Celsius degree. And then most of the glucose, which is C6, H12, and O6, this glucose is going to be used to make lots of ATPs and also NADH and then FAD. These are actually, these two are also going to be used to make ATP. So adenosine triphosphate, ATP is a source for our energy, our body. And then most of actually energy in this process is generating the heat. And the heat is actually essential component to maintain our body temperature to be 37 Celsius degree. Since you are all single, so no one is married except me, so you may have no idea about the raising the baby. But the most difficulty part from the baby for the sickness is the high temperature, high body temperature. So if there is like 37.8 or 9, then that's kind of okay. But if it starts to reach beyond like 38.5 to 39, sometimes it can go up to 40 Celsius degree. Then it's high fever. And those fever can actually cause a lot of problem for the body. So maintaining temperature is very important. And also for the, when you are using the laser for treat something in your body, also many of energy can be used to generate heat in our body. And then it can generate heat up to like 42 Celsius degree. And then in this case, actually our body doesn't really feel bad. So nothing really so bad thing for our body. But if the temperature in our body is going up to 50 Celsius degree, then that is called as a hyperthermia. So thermia is, thermal, and that represents the heat. Hyper means that, plus, more than plus, and the hypo means that, less. So hyperthermia, so means that you have a higher temperature. And then up to 50 Celsius degrees is called as hyperthermia. During this temperature, what happens to our body is the molecules and also those cells in our body are going to go under conformational change. And also the binding among molecules can be destroyed. And also the membrane that consists of the cell or mitochondria, the membrane structure can be also changed. So if you are under several minutes of hyperthermia, then it goes to necrosis, which means that going to make cell to be death. So for the brief time, exposure to the hyperthermia is going to be okay. But if you stay there for a few minutes, then that tissue can go under necrosis. And then if the temperature is going beyond 50 Celsius degree, the enzyme in our body is going to have a reduced activity. And then this will also cause the reduced energy transfer within the cell, and also it will also reduce the mobility of the cell. And also it will disable certain repair mechanisms of the cell. So actually our body and our cell, they have a self-repair mechanism. But if the temperature is beyond 50 Celsius degree, then they will disable the repair mechanism. And also temperature is beyond 50 Celsius degree, then it will further reduce the surviving cell fraction. So now let's raise to the 60 Celsius degree. For the 60 Celsius degree, what happens is that the proteins and the collagen, they are denaturizing. And then the tissue will be coagulated and the cell will be die. And because of this denaturation of the protein and collagen, and also coagulation, it makes scattering change. And then the tissue became kind of pale color. So laser-induced interstitial thermotherapy, which will be discussed later, this LITT is targeting the temperature for just above 60 Celsius degree to make the cell death. If the temperature is going beyond 80 Celsius degree, then the permeability of the cell membrane is increasing. So we know that cells are having the membrane, right? And then membranes are having double layers. So outside is basically water-like, and the inside is lipophilic, which means that they prefer lipid. And they are having a few of the ion channels to allow the ion exchange, but other parts are very dense. They are highly dense, and then it doesn't allow something to going through. But because of the high temperature here, this membrane start to break down, and then it allows either inside go out or outside goes in without having going through the specific channels, so that there will be no more control for the traffic. And this will destroy the equilibrium of the chemical concentrations. So sodiums and then chloride and then potassiums. Those are all should be calcium. These need to be very well controlled. However, there will be breakdown. If the temperature goes to 100 Celsius degree, then you all know that the water in our body start to vaporize. And for the vaporizing, you need to provide at least 2000 kilojoule per kilogram of the water to make water to be vaporized. So this value itself is actually very high value. And then this large Q vaporization value is actually providing advantage to our body, because by having this vaporization, the energy, this vapor, making the vapor from the water liquid water, it requires to absorb lots of energy. So it can remove the excess heat, and then it can prevent any further increase of adjacent tissue temperature. So what does that mean is, when you have a tissue and then giving a laser, and then our body has lots of water, like 60% to 70% is water. And then when the laser is irradiated to our tissue, then it will start to raise the temperature. But to make higher than 100 Celsius degree, they first had to vaporize water molecules here. Once they vaporized all the waters in the tissue, and then the excess energy can be used to increase the temperature. And also at the 100 Celsius degree, the gas bubble can be formed, and then this bubble can be exploded. And then they will cause the mechanical rupture and also thermal decomposition of tissue fragments. So the temperature increases only if all the water is vaporized. And then, but still you have a laser exposure is continued. Once the temperature is going beyond 100 Celsius degree, which means that the laser vaporized all the water in the tissue, but still the laser is providing energy to the tissue. In that case, the carbonization is occurring, and then you can see the smoke. To prevent this carbonization, you can use the water or some cooling gas from the outside to prevent carbonization. So simply, carbonization is something that when you cook meat, when you are cooking the steak, and then you can see the color of the meat or steak is originally kind of red color, and then start to becoming a little bit brownish. And then if you forget to flip over, and then you can see that later the bottoms are actually burned, and that burn of the meat is basically carbonization, so making the black. And then you can also see the smoke comes if you're burning the meat. And if the temperature is going beyond 300 Celsius degree, then they can actually melt the tissue. but they will be depending on the target materials. For the soft tissue, of course, 300 Celsius degree will be high enough to melt down the tissue. But for the tooth, which has just like bone, they have a more higher melting point. So that you need to have a more higher temperature to melt down the tooth. So this table is a summary. And then this is also one of the popular questions in the exam. I'm telling all the questions to you, so you need to check. Okay, I had to really read carefully about this one. So this table is summarizing about the effects of the temperature on the biological tissue. So when there's a temperature is going beyond about 60 Celsius degree, as you can see here, that causes the coagulation. And the coagulation is basically going to make the fluid into thickened mass, or for the blood case, making clot. So tissue coagulation in general means that you are stopping the bleeding. That can be kind of understood as a coagulation for the tissue by using the laser. So here is the examples of the tissue. This supposed to be shown as a color, but I don't know why the textbook is showing as a black and white. But here you can see those black dots. Those dots are representing the nucleus of the cell. And then maybe these could be the blood vessels. And here you can see is the laser was irradiated to these positions. And then they burnt tissue, which is thermal ablation. So giving a high temperature, they basically burnt the tissue, and then tissue has been gone. Phew. And then these are the leftover tissue. However, you can see quite big area surrounding this laser irradiated area became kind of black color here. And then especially close to that area is really black color. So those area right next to the laser irradiation is blackened, which means that they are burnt. And then it is basically carbonization. So this part has been carbonized by the laser due to the high temperature increase. And then these kind of gray color area are representing coagulated tissue. So they are not burned. However, they still also had high temperature, such as the more than 60 Celsius degree. And then they cause the cell to be death in this large area. And then this proves that when you are using the laser, this can be a side effect. So we want to minimize, or we want to avoid this carbonization. We also want to avoid the volume of the coagulation of the normal cell. So let's say that this was originally like this, and then they had a tumor in this region. And then I want to basically remove this tumor by using the laser thermal interaction. So I use the laser, pew, and then making temperature goes up so that I burned all the tumor tissue. However, you can see that surrounding normal tissue has been damaged. And then for the clinician point, we want to minimize this, the coagulated area, and also those carbonized area to be minimum. So the top one is using the continuous wave ND-YAG laser with the power of the 10 watts. and then that made the coagulation and the carbonization around the area. And then the bottom one is the human cornea. And then that has been coagulated with 120 pulses of the erbium YAG laser. And then first duration was 90 microsecond. And the repetition was every 1 hertz. And then here you can see, of course, these two are different tissue. So it's hard to actually direct comparison because each tissue are having different thermal property. The top one is uterine and the bottom one is the cornea. But the bottom one, by giving a pulse, and then top one was giving the continuous wave. So it's not pulse. So continuous wave laser was causing big area of the coagulation plus carbonization. But bottom here, you can see you have a very clear, this black color, which means that they are the carbonized tissue. However, you can see surrounding tissue doesn't really look like having any coagulation. So that proves that the bottom one, by using this pulse laser, was causing less side effects for the normal tissue. Now you are seeing the color. So here, as you can see, when you were using the laser, and then those parts has been ablated, disappeared, so gone. And then coagulation is shown as this much. So you can see by looking at the H&E staining, the colors are different and the structures can be shown here. And you can see that those areas are probably having the thermal effects from this laser irradiation. Again, shown on here, by using the laser so that they removed the tissue, so which is thermal ablation. But you can see that surrounding that area like this, these are having different color compared with the other surrounding tissue. And those area represents coagulated tissue. Luckily, this doesn't have any carbonized tissue, which means that actually the laser here, they were using very short pulse, mostly shorter than 1 microsecond pulse for the treatment. The bottom one is showing about the structure of the skin. So skin can be divided into epidermis, which is about like 200 microns, and dermis having a few hundreds microns thickness. And under the dermis, there is a hypodermis tissue. And here you can see epidermis doesn't really have any pain. So when you are having micro needle for the drug delivery, and then those micro needles are actually going right under this epidermis so that it doesn't cause the pain, but can deliver the drug better into under the skin. In dermis tissue area, you can see that they are having some micro blood vessels. And then for the hypodermis tissue, you can see the kind of major blood vessels are going under and also fat layers. And then sometimes they're having a sweat gland, and those are here. And also those hair follicle can be also in the hypodermis area, and sweat gland here, and the fat. So look at the vaporization. Can you imagine what is this on the right side photo? Taeyeon, can you guess what is this right side photo? It looks like, you know, kind of sci-fi movie when you are going into some Mars or some other planet, and then totally different the environment can be seen here. Actually, the bottom one is actually the zoomed image from the top one. So same thing. But top one is basically from the surface of your tooth. Oh, wow, is this tooth? So they were using like 220 times X of the, I guess this is SEM. So basically the scanning electron microscope. So using the electron microscope, it can visualize very details of the structure here. And you can see that by giving 20 pulse from the erbium YAG laser, and then each pulse was having 90 microsecond with 100 millijoule, and then repeated for every second. So every second, 90 microseconds of the erbium YAG with 100 millijoule of the energy, and they're giving 20 pulse, doom, 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 20 times. And then actually that provides high enough temperature to cause the water molecule in the layer, so-called as a stria of the reticulus. So this is also interesting because I never thought that the tooth has a high water contents. But the tooth, if you look at the cross-sectional structure of the tooth, this part is basically enamel, right? And then within this enamel, actually, there are some layers here. And that layers is called as a striae of the reticulus. And then those layers are containing a relatively high amount of the water. So what happened to this tooth was by giving a laser, and that laser was vaporizing water molecule in the stria of the reticulus layer. And that water molecules is going to absorb the laser energy and then becomes the vaporization. So when the liquid becomes vaporized, then there will be a volume expansion from the liquid to the gas. So the volume expansion is going to make a kind of mechanical push away, for the surrounding tissue. So that's what happened in this area. So when there was a laser, and then the laser was heating up water molecule in the stria of the reticulus layer, and then water molecules become vaporized, and the vaporized water molecule will have an expanded volume, so that makes a crack, as you see here. So you can see the cracks here. Look at detail. So multiple layers of the enamel. Now you can see the separation between each layer. That also has been done because erbium YAG laser is generating about 3 micrometer wavelength of the laser. And the water molecules are having high absorption at the 3 micrometer because of that vibration mode is in that 3 micrometers. So that induced increase in pressure of the water, and then they expand the volume, and then they make localized micro explosions. And then they made this separation of the layers. So it's amazing that using the laser, you can also make the tooth, which we believe that one of the most strong, hardest tissue in our body can be easily broken. So here, sometimes other literature are saying that vaporization of the water is sometimes referred as a thermomechanical effect. So by giving a high temperature and then making the volume, expansion, it can cause the mechanical damage to the surrounding tissue. So this resulting ablation is also called thermal decomposition. And this thermal decomposition is not same as the photoablation, which will be discussed in the maybe next week. When you have a more higher temperature, and then it can cause the carbonization. And then this one is actually from this tooth. So from here tooth, you are giving the many pulse, or sorry, in this here actually different. So here there are two different types of tissue. The top one is the tumor. So tumor on the skin has been carbonized with a continuous wave CO2 laser. So, but this carbonization is something that we do not want to have during the laser treatment. The bottom one is giving the continuous wave CO2 laser to the human tooth. And that tooth also has been carbonized, as you can see from this photo. So carbonization is going to happen when all the water molecules are vaporized, and then nothing more to be vaporized. And then the leftover tissue will be basically burned, and then becomes the black color. So when the temperature is above 160 degrees, then tissue starts to carbonize, and then it makes blackening of the color. And we do want to avoid the carbonization in any case, because carbonization means that that tissue area has already been necrotic tissue, which means that tissue. And also it can reduce the visibility during the surgery. So when the area is becoming blackened, then you cannot actually see the details of that tissue area. So this one is showing the examples of using the laser for the surgery for the epilis fissuratum. This is kind of a pseudo-tumor growth of the soft tissue. And then as you can see here, this part can be actually removed by using the laser. And then, but in here you can see it left lots of the carbonized tissue area, which is not the desired one. So we need to avoid to make any carbonization of the tissue. When you have a more higher temperature of the tissue, then basically it will cause the melting. So we were having the coagulation with a 60 Celsius degree, vaporization for the 100 Celsius degree when there are water. But when there's no water, then 100 Celsius degree is going to cause the carbonization. And then if you have an even more higher temperature, then it can start melt the tissue. This photo is also from the tooth, so human tooth. And then that has been melted by using chromium yak laser. And then with a 3.8 microsecond and the 18 millijoule, and then every 1 second, but giving 100 pulse. So giving 100 pulse, one pew, 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 like every 1 second, pew, pew, and 100 times, so 100 second total. And then that accumulates temperature in this area, and then finally building up the high enough temperature, and then to melt this tooth. And you can see those, spots are basically when the tooth were melting down, the gases could be escaped, and then the escaped spot can be shown here as many of the dots here. It's like in lava when there is a lava explosion. Also, this melting process can be used to remove the lipid. So I'm also getting more bigger, the belly these days. So many people try to remove the fat by giving the diet, by having a diet, or by doing the exercise. But sometimes there is limitations for doing that. So in that case, you can have a surgery, and then I guess you have seen those surgery, right? So making a hole under the skin of the belly, and then basically inserting some kind of probe, and that probe can be actually RF powered probe or this laser probe, and then going in, and then under here it start to illuminate the laser, and then melting the lipid around the area, and then pushing many different ways, and then reduce the fat. And that is the called as laser lipolysis. So here the left two photos are representing the normal adipose tissue, the fat tissue. The right two are representing after it goes under laser lipolysis. By using the first about 40 to 80 hertz for the ND-YAG laser, which has a 1064 nanometer with a relatively high power. And then those lasers can be used to remove those adipose tissue. They melt down like this. So now we will go over a little bit more details about this thermal interaction. So for the microscopic level, thermal effects are from the absorption. And then that absorption can be from molecular vibration or rotation bands, followed by non-radiative decay. So here, non-radiative decay is mostly representing heat also generation. These thermal effects are from the absorption process, and the absorption is happening by interacting with the molecular vibration or molecular rotation bands. So two steps of the temperature increase process can be shown here. So the first one is absorption process. So when you have a molecule and having a h nu of the photon energy, and then this A will be in an excited state, A star. And this excited state A star needs to go back into the ground state A. And then one way is by interacting with the surroundings and then giving the energy to the surroundings by providing more of the kinetic energy. And then this extra delta E can be used as a heat generation. It's something like, kind of, you can imagine as a friction. So when there is a high friction, so when you want to make a fire by using the wood, and then under the wood is kind of giving a friction with another wood plate. And if you give a high friction, then they can cause the heat generation. So you can understand this as the kind of friction energy will become into the heat. And these two process is relatively very efficient in our body when you are using the laser. That is because our tissue has a very wide range of the vibrational states of the biomolecules. So which means that our tissue doesn't really observe the light energy in a specific wavelength. It has a wide range of the wavelength because the vibration states are also in a wide range. So we have a wide band of the wavelength to observe the photon energy. So we have a high absorption efficacy for our body tissue. And also the providing energy to the tissue from the laser, such as the erbium YAG or ND-YAG or argon fluoride, they are having relatively high energy. So 0.3 or 1.2 electron voltage, or sometimes go up to 6 electron voltage. compared with the molecules at the room temperature are having about 0.025 electron voltage as a kinetic energy. So those molecules in the room temperature are having low kinetic energy. And then if you are giving the laser to the tissue, and then those excited tissue are going to deliver their energy to the surrounding molecules. And then the surrounding molecules are gaining extra of the kinetic energy. And that extra of the kinetic energy can be used to generate heat. So when we look at the tissue damage, the spatial extent, and then the how much degree of the tissue damage, these are all going to be depending on the magnitude of the heat and how long exposure time, and then where the placement of the deposited heat inside the tissue. So the deposition of the laser energy can be a function of the laser parameter. So by controlling the wavelength, power density, or exposure time, and also in the real application, the how big or small spot you are using, or how fast you are repeating for the pulse laser. These are all laser parameter. But for the tissue part, tissue optical property, mostly absorption and the scattering coefficient, these are going to affect for the deposition of the laser energy in the tissue. So thermal tissue property, such as the heat capacity or thermal conductivity, they are the primary parameters of the tissue to describe the storage and also transfer of the heat. So when the heat is generated, so there are very high observer here, and then this observer is observing the laser energy and then producing the heat. And then heat capacity means that how much this tissue hold the heat. And then thermal conductivity means that how fast this tissue can deliver the heat into surrounding tissue. So absorption in the biological tissue is mainly because of the free water molecule in our body, and also proteins, and then pigments, and also other macromolecules. And then it is following the Lambert's law. So Lambert's law means that in the distance of the z, the intensity at this z point is going to be the maximum intensity multiplied with the exponential function of the alpha. Here, alpha is absorption coefficient, and the z is the length. So mentioned many times, when the laser is coming here, and then if this is the z, and at one point g, let's say g1, then this g1 point, the intensity is going to be this I0 exponential minus alpha and g1. I0 is going to be intensity at the surface in this case. So that means that light intensity is exponentially decaying as they are traveling in the tissue. And this alpha, which is the absorption coefficient, will determine how fast this will decay or how slowly this will decay. So low absorption, slowly, and the high absorption, very fast decay. And we all know that this absorption coefficient is also depending on the wavelength. That is because when there is atoms, the ground state and the excited state for the singlet, and then also there is a triplet excited states. And singlet states also can be multiples. So 1s and 2s and 3s depending on the atom. So for the hydrogen, it's a very only single 1s, but as the atomic number goes bigger, then you have a multiple of the singlet states of the excited level can be existing. And each of the singlet, these excited states can be also divided into multiples of the vibrational energy level. So there are many different chances for the absorption. And then those are depending on the atom. And because of that, the absorption coefficient is going to be depending on the wavelength, because each distance from the ground state to the excited states are representing specific energy gap. And then for the light, h nu to be observed by this atom or molecule, then they had to be matched with this delta E with the h nu. So each molecules are having their own specific absorption spectrum depending on the wavelength. For the thermal interaction, the most important molecule in our tissue is the water. So water absorption plays the most important role. So the left one is showing the water absorption spectra from the UV range to the 10 micrometer here. So here we can see these are the visible range. So about 350 or 400 nanometers to about up to 700 nanometer or 650 nanometers. So these are having very low absorption by the water. So that's why when you have a water, such as this water bottle, because of plastic, you cannot actually easily see through. But if this was the square shape of the glass, then you were easily able to see through the water. Right? So water has a very low absorption in the visible range, so that water looks transparent to our eyes. But as the wavelength is increasing, especially more than 1 micrometer. So before 1 micrometer, there is a one small peak, which is about 980 nanometer. And then going more like 1.3 and about 2, and then about 3 micrometer. And then about like 4.5, and then about 6 micrometers. So here you can see these water molecules are having highest absorption at the around 3 micrometer range. So that means that when you are using the laser for the 3 micrometer range, then that laser energy can be easily observed by our tissue. So here, the table also shows the absorption coefficient alpha, which is mu A, and the absorption length of the air, which is the 1 over actually mu A. So here you can see this air means that like 10 centimeter means like when the light is traveling 10 centimeter in the water, then this will be observed. And then here we can see for the 514, it can go up to 3 kilometer, right? And the 633 is 340 meter. 350 is 430. So this visible range, basically water is very transparent. And then you can go through the water, see through the water. But as the wavelength is going increased, especially here, 2.9 micrometer, and then 0.00008 centimeter. So that means the 0.0008 millimeter. And then that means that 0.8 micrometer. So in the wavelength of the 3 micrometer, you can only see through water with a 0.8 micrometer thickness. Beyond that, you cannot actually see through the water. It will be very opaque. It will not be transparent to the 3 micrometer anymore. So have a very high absorption. The main water absorption is around 83 micrometer, and then that is because of the vibrational mode of the water. So water has 6 different vibrational modes that we mentioned before. So mostly like symmetric vibration or asymmetric vibration. And then the frequency has been shown here. And then by using this frequency value, the vibrational frequency, you can estimate about what will be the wavelength corresponding to this frequency. So since the light speed is like 300 times 10 to 6 meter per second, and the refractive index of water is 1.33, which means that light speed in the water is going to be 1.33 times slower compared with the light speed in the vacuum. So wavelength definition is the speed, light speed in that medium divided by the frequency. So you can have a 300 times 10 to 6 meter per second divided by 1.33 and divide by those frequency value. And then it will give you some wavelength conversion of the frequency value. I have calculated, and then actually it's not exactly 3 micrometer. So there are some differences, but as I said, water has like 6 different types of the vibration mode. And then these are actually 2 examples, and the other 4 needs to be also mentioned to find out the exact wavelength of the water. But anyway, so by using this vibration frequency, then we can find that the water absorption can happen at the close to 3 micrometer wavelength. So by using the erbium-YAG laser, which has a 2.94, and erbium YLF at the 2.8 micrometer, and erbium YSGG at the 2.8 micrometer, and also holmium-YAG at the 2.12 micrometer, they can be used for giving a thermal interaction for the laser. So, I mean, 3 micrometer is very high, but 2 micrometers are also having relatively high absorption by the water. So you can use those. Okay. So now we will go over about the some modeling for the thermal effect in the tissue. So when the laser or some other light source are coming into the tissue, then the laser parameter and also optical tissue parameter, both are going to determine basically generation of the heat. So more high power and then more better wavelength for the water absorption and longer exposure time, they will have a more higher heat generation. And also if the tissue has a higher absorption at that specific wavelength, then they will also allows to have a high heat generation. So once heat is generated by interacting between laser and the tissue, then this heat generation, generate heat can be transferred to the surrounding tissue. And then for the heat transport, the important parameter is going to be thermal tissue parameter. And then many of the thermal tissue parameters among many of the thermal tissue parameters, the heat conductivity and the heat capacity, those 2 are the most important thermal tissue parameters that determine heat transport. And then basically this heat is going to cause some effects. It can cause the coagulation, when the temperature is around 60 Celsius degree. It can also cause the hypothermia for the 50 Celsius degree. And then basically water vaporization at the 100 Celsius degree. And then if all the water molecules are vaporized, then the carbonization will happen. And also that damage of the tissue will be depending on the type of the tissue, because for the same temperature, the fat tissue versus maybe our tooth will have a different effects by the same temperature. So these are the basically three components for the thermal effects when you are using the laser. So between the interaction with the laser and the tissue, you can generate heat. And those generate heat will be transported to the surrounding tissue. And for the heat transport, the thermal tissue parameters are going to play very important role. And depending on the type of the tissue that generated heat or transported heat can cause different tissue damage. So let's look at the heat generation first. So for the heat generation, we are assuming that tissue is having a slab, and that the slab of tissue is exposed in the air, and then there will be a Gaussian-shaped laser beam will coming. So here you are seeing the examples of that. So tissue is here, and then you are assuming the tissue in here is a cylindrical shape, and the laser is coming with a Gaussian shape, and then having a width of the 2W. For the Gaussian beam, can be shown on this figure. So by using the kind of lens, you can make a focus like that. And then here is the most narrow, the width of the beam. And then that is the called as a beam waist. And here the radius is notated as a W. And then for the plus and minus from this focal length of the square root of the 2 of that radius. So up to here is kind of focus depth. So that means that for the camera point, when you are having the lens and when you are seeing something, if your focus depth is, let's say, maybe 2 centimeter, and then when you were making a focus at the, let's say, 1 meter distance from the lens, and then this focus of depth is 2 centimeter, means that you can see 1 meter is like 100 centimeter. So you can see 98 centimeter to 102 centimeter very clearly without having a huge blurriness. However, when you are having an object either shorter, closer to the lens, or very far from the lens, those areas will be not focused well, so that it will become kind of blurry. So these days, many of the cell phone camera has functions of like using this. 승리야, are you hungry? This will be really funny because this is all being recorded. And then suddenly we see that Seung-young is eating some breakfast. It's okay, as long as you pay attention. I understand. You must be so hungry. So if the focus depth is 2 centimeters, we have a very narrow range to have a clear image. But if you have a like this focus depth is like 20 centimeter, then you can have a 90 centimeter to 110 centimeter range of the objects can be or were clearly visualized by the camera. Okay, anyway, so when you are making the laser, so the laser can be generated, and then by using the lens, you can also make the laser to be even more focused. And then when you are looking at the kind of this plane, and then look at this. Let's say this is the maybe x-axis, the x-axis. In the center here, you have a highest intensity, and then it goes down like that. So this, so this is the profile of the laser beam, and then you can see that the laser intensity is not actually same throughout this x-axis, and then it has a Gaussian shape of the profile. So that's the meaning for here as a Gaussian shaped laser beam is coming to the tissue, and then overall the beam width is 2W here. And then we know that the electric field of the light, the amplitude of electric field can be shown as a E, and then this electric field will be depending on the R here as R is the radius, and then Z is the depth into the tissue, and then depending on the time T. So that electric field is described as electric field 0, which maximum electric field, and then 2 of the exponential function. And the intensity at the R, Z, T factors can be also shown as the bottom one. Since the relationship between electric field and the intensity is shown as this. So intensity is 1/2, and the epsilon 0, which is dielectric constant, depending on the each different materials, and C is the light speed, and then E sub 0 and square. So simply, intensity value is proportional to the electric field square. So that's why when we come back here, the electric field is shown on the top, and the intensity value is simply square of that. So that will give I0, and then square and square, so that it will give 2 here, and then cancel, and then make A here. So intensity at the RZT can be described as a maximum intensity of the light, and then 2 of the exponential function. Here, both are basically decaying function. So it will be decay depending on the time. So as time goes, it will decay. As light travels in G direction, it will also decay. That follows the absorption coefficient. And then when the light beam is also traveling in the R direction, that also will be the decay. And that will be depending on the beam width, the W, and then overall R position. So by looking at this one, and then here, the tau is the pulse duration time. So when the time is 0, so t is 0, so this will be 1. And then if r is w, so r is w, then and also z is basically 0, which means that at here, so g0 means that only the surface, and then only in the r direction, then the intensity is going to be 1 over e squared. So this will be -2. So I0 exponential -2. So that will be 1 over e squared. And also either r is 0, so mean the center of the beam. And then if the t is the tau over 2, so it means that if the pulse duration is 1 microsecond, then if the time is 0.5 microsecond. So if you put the t as 1 over 2, tau over 2 here, then they will cancel out. And left over is 2. So same thing, -2. So it will give the also 1 over e2 square of the I0. So at the R is W, which means that at this point, so center is 0, and then R goes to W, which is the radius of the beam. So at the point here, the intensity will become 1 over e squared of the I0. And then if the time is half of the pulse duration at this point, G0 and R0, then the intensity also will be reduced to 1 over e squared of the I0. So E, we just mentioned that between the electric field and the intensity is related by this relationship. So basically intensity is the square of the electric field. And then for this model, we ignore scattering property of the tissue. By having the scattering, they can be very, very complicated. So for this model, we assume that scattering is kind of negligible, and the only absorption is the major optical property of the tissue. So when the laser is coming to the tissue, then heat will be generated, and then it will be also deposited from the absorption of the light in the tissue. So light flux in the G direction, then the local heat deposition per area, per time in a thickness of the delta Z. So we have a cylinder of the tissue, and then you have a beam width of the 2 omega, which is from the laser, and then traveling into this G direction. And then when you look at the very, very small thickness, delta Z, and then within this delta Z, the heat deposition per area of this area, and then per time in this delta Z thickness can be described as a S, RGT, depending on R, depending on Z, and depending on time. That can be basically IRGT minus IRG plus delta Z plus T. So here is the Z, and here is Z plus delta Z. So light intensity at the Z position minus light intensity at the Z plus delta Z position. So difference between those two positions of the light intensity is basically heat deposition in the delta Z. Okay, so I will stop here for today, and then we will continue on this heat generation model on this Thursday. However, this Thursday, I need to go to the Asan Hospital for the business trip meeting, business meeting. So I will record the material, and then I will upload to the YouTube, and then I will make it open to the public starting at 9 a.m. so that you can come in and that you can watch the YouTube and then try to understand about the materials. So have a nice lunch today, and also Taehyun, hope that you can have a better some camera next time so that we can see each other. Taehyun, can you hear me?
Yes, yes.
Okay, good. All right, so
Hello,
everyone.
Professor, you just uploaded last 2 or 3 classes. You will upload this recorded class.
So uploading last 2 or 3 slices.
No. Last 2 or 3 class you doesn't upload
Oh,
it.
yeah, I didn't. Yes.
Yeah.
Right. I did not upload the last 2 or 3 classes. I didn't know you were pay attention to the uploading, but I will. But as I mentioned before, I forgot to record the one time.
Yeah, one class.
So
Yeah.
one time I may need to re-record myself, but I will upload the other previous 2 classes in the YouTube. Okay, so thank you everyone, and have a nice lunch, and then see you maybe real time on actually one more thing. So next week is actually midterm exam week. And then as I promised in the first class, there will be no midterm exam. Oh, Nur seems like very happy. But actually that can be worse because there will be more materials that you have to cover for the final class. So it's good and bad actually. And then, so we will actually come back on April 27 for the class in the real time. But for this Thursday will be on the YouTube. Okay, so thank you everyone, and see you next time.
Thank you, Professor.
Bye.
Thank you, Professor.
Thank you, Professor.
Mm-hmm.